If the universe is infinite, and even if there exists a multiverse with an infinite number of universes, does that mean that somewhere else there exists a copy of Earth, and even an exact copy of you, and possibly an infinite number of these copies? This idea is popular in various manifestations of mass culture, in books, comics, movies and TV shows, games, and even in songs. Deep inside of the parallel universe. Excuse me. Singing is not customary on my home planet, but I do love your Earth music, especially the Red Hot Chili Peppers. Here, someone might say that with a truly infinite universe, this is natural and possible. It is so. But it's interesting to note the leap of thought from the fact that, as of now, Earth is the only place in the universe where life is known to exist, to the existence of infinite copies of our planet. Probably the thought that there is another you somewhere, and a you whose life differs slightly, is not very comfortable and is somewhat frightening. But if there is some basis for this, what does science say about it? And can your copies actually exist? Interestingly, the answer is not that simple and has several layers, starting with whether the universe is indeed infinite, and ending with the concept of the multiverse, which may also be of several types. And that's not all. We will discuss this today. Let's try to give at least approximate estimates of how far away your nearest copy might be, and whether you could meet them, well, if they exist. Call me Cosmo, and you're watching Space Made Simple. Let's start with the first and most intuitive level, which is likely what most people think of when they ask this question. We have a universe. It is infinite, which means sooner or later, you'll encounter your duplicate there. And immediately there arises the question, is the universe truly infinite? The short answer, we don't really know. There are some estimates and assumptions, but essentially, we have to make certain assumptions right from the start. I must warn you that this is closely related to the geometry of the universe, whether the universe is flat, open, or closed. Even if it is flat, it can still be finite. Let's clarify what all this means. Remember, when talking about the shape of the universe, three main possibilities are usually considered. The universe could be flat, open, or closed. The geometry of the universe, or space-time, is one of the key points in cosmology. Depending on what space-time is really like, it determines whether the universe is finite and its ultimate fate. Will it continue to expand indefinitely, or, conversely, will it collapse back? Visualizing how three-dimensional space can have any specific shape is problematic with your brain, so we use two-dimensional analogies to give at least some intuitive understanding of what we're talking about. When we talk about the shape of the universe, often when discussing a flat shape, the analogy given is like a two-dimensional sheet. Although we can't imagine what this looks like in three-dimensional space, we can still make very specific conclusions. Two parallel lines in such a universe will never intersect, and if we draw a triangle in this universe, the sum of its angles will always equal 180 degrees. If we start moving in one direction in such a universe, we will infinitely move away from the point from which we started. Such a universe expands infinitely, meaning, starting from the Big Bang, it will grow indefinitely, and it is infinite. And again, a flat sheet is just a two-dimensional analogy. Right now, I can move forward, backward, right, left, and up, down. In the universe we live in, if I remove the ability to move, say, up and down, I would be as if living on such a sheet. In this analogy, the universe is just like that, only it is not limited by four sides, but infinitely extends in all directions. And in this version of reality, the same is assumed, only in all directions. The universe can also have an open geometry or have negative curvature. Such a universe is also called hyperbolic. As a two-dimensional analogy, consider something like a horse saddle. Lines in one area, being parallel, eventually diverge. The sum of the angles in a gigantic triangle is less than 180 degrees. In this case, the universe is also, broadly speaking, infinite. But the first hints of possibly, at least hypothetically, seeing a duplicate arise in a closed universe, which seems to be finite. However, these are not the duplicates we were talking about at the beginning. This refers to closed spherical geometry, in contrast to the flat sheet. Here we have a two-dimensional surface of a sphere, not a ball with all points inside, but a surface where all points are equidistant from the center. Again, this is just a two-dimensional analogy. The main thing is that in such a universe, initially parallel lines will eventually meet at one point, and the sum of the angles of a huge triangle is more than 180 degrees. Moreover, such geometry leads to the notion that if we once started moving in one direction, we could, in principle, end up returning to the point from where we started. Suppose such a universe was very small, say, 10 light-years in diameter. One could imagine that by looking through a very powerful telescope in a certain direction, if nothing obstructed the path of the photon for 10 light-years, we could see Earth as it was 10 years ago. And somewhere there, you would be walking from 10 years ago. This is not a duplicate, but just photons reflected from Earth 10 years ago. Well, another thing is that due to the peculiarities of such geometry, the shape and size of what we see might be unexpected. There's a cool article on this topic with awesome illustrations. I'll leave a link in the description. However, the universe is not 10 light-years across, and we do not see copies of Earth, nor any section of space, possibly because the universe is so vast that light has not had time to return, but more likely because its shape is not closed and finite. But the three forms I just mentioned are not the only possible options. It is also said that the universe could be flat, but at the same time finite. For this to be the case, it could, for example, be in the shape of a three-dimensional torus. But again, we can't imagine the surface of a three-dimensional torus, so here we use a two-dimensional analogy again. In such a scenario, as with the flat sheet, parallel lines will always remain parallel and will neither converge nor diverge. However, this space closes into itself, and moving in one direction or another, we would return to the point from which we started. This would apply to light as well. If we lived on the two-dimensional surface of such a torus, and such a universe was small enough for light to have time to return to us, then it would have multiple circular trajectories by which light could reach us, and we would see copies of ourselves and more in different directions. Well, visualizing this in three-dimensional space is somewhat challenging. Obviously, we don't see anything like this, and the universe is not that small. But if the universe were closed, the geometry itself would allow us to see a copy, or rather, an image. Another matter is its real size. This would not be possible in practice. And now the main point. What is the universe really like? Scientists can't say with 100% certainty yet, but still, most of the data indicates that it is as in the first example, flat and probably infinite. Although it could be so large that in our local segment of the universe, we can't see any curvature, and it appears to us to be flat like a sheet. But in reality, it might be a closed sphere. Then, according to some estimates, it would be at least 250 times larger than the observable part of the universe. But there's still a significant chance that it is infinite. And here we can't do without the concept of a multiverse, at least in some form of it. Soon on the channel, I'll release an episode about cosmic horizons and the boundaries of the observable universe. The observable universe is a unique bubble with us at the center, having a radius of about 46.5 billion light-years. Of course, we're not actually at the center of the universe. The size of this bubble is determined by how far light has traveled to us since the beginning of the universe, 13.8 billion years ago. Why is the radius of the observable universe more than 13.8 billion light-years? It's due to the expansion of the universe. Light doesn't simply travel from point A to point B. but does so through constantly expanding space-time. We don't know what lies beyond the particle horizon, and how many more universes there might be. Suppose if the entire universe suddenly turned out to be not much larger than our observable universe, there would be no copies of Earth and us in the universe. It would be too small for that. Since there is a limit in the form of a horizon, and we live in a limited section of the universe that is expanding but beyond which we cannot see, this is where discussions about the multiverse begin. Renowned cosmologist Max Tegmark, who you may have seen in some science popularization shows, proposed a classification with 4 types of multiverses. The simplest and least controversial type is the first-level multiverse. We live in our bubble of the observable universe. Our bubble and its boundaries are essentially determined by us, the observers, at its center. If beyond its limits there's just more of the same expanding universe, then there, most likely, continues the same universe with the same laws of physics and fundamental constants, with the same galaxies, stars, and planets. If beyond the limits of our observable universe, say at a distance of 100 billion light-years from our particle horizon, there's some other observer, then he or she would have their own bubbly. It's as if we exist in the same space, but we are so far apart from each other that we have no way to interact, as if we live in different universes. Essentially, this is exactly what we discussed at the very beginning. Could our copy meet in such a universe? To understand the very idea why copies can even arise, Max Tegmark in his article about the levels of the multiverse suggests the following. Let's simplify our universe to the maximum. Make it 2-dimensional and imagine that there are only 4 particles in it. For such a universe, there are 16 possible configurations of how these particles are arranged. If in the first-level multiverse there are more than 16 universes, then beyond that, particle configurations begin to repeat, and full copies of the first universe start to occur. Now, simply transfer this analogy to our universe and apply the same logic. Another matter is that it is 3-dimensional, and there are slightly more particles. Here's a jar filled with colored candies. Currently, all the candies are arranged in it in a certain way. No matter how many times you shake this jar, the chances that all the candies will return to exactly the same position are incredibly slim. It's hard to imagine. Well, in the universe, according to some estimates, there are up to 10 to the 82nd power atoms in the observable universe. That's a 1 followed by 82 zeros. The number of subatomic particles, according to Max Tegmark's article, is estimated to be 10 to the 118 power particles. To get a complete copy of our observable universe, you would need such an unimaginable number of particles to have exactly the same configuration and complete history of interactions from the very beginning of the universe over billions of years. Intuitively, this seems absolutely impossible, and yet, theoretically, you can calculate the number of possible configurations for both 4 and such a quantity of particles, and then calculate what volume of space is needed for the configuration to start repeating. In Max Tegmark's article, it is estimated that your identical copy should meet in the universe through 10 to the 10th to the 28th power meters. If you enter this value into the Google calculator, it will freak out and say infinity. Although, of course, it is not infinity. It's such a large number that it's impossible to even imagine. 10 to the 10th power is a number with 10 billion zeros, while 10 to the 10th to the 28th power is a number with 10 octillion zeros. And in light years, I'm not even going to attempt to convert that. With such values, whether meters or light years, a few zeros here, a few zeros there, that doesn't matter at all. But through a distance of 10 to the 10th to the 92nd power meters, there could be a sphere with a radius of 100 light years identical to ours, and through 10 to the 10th to the 118th power, there could be an identical observable universe. Naturally, these are only rough estimates, but in any case, If there is a region of the universe that has formed exactly the same, and there is an exact copy of you, these are unimaginably vast distances that, at most, they are suitable for philosophical contemplation. Another matter is that there is an opinion that such copies do not necessarily have to exist. At first glance, it seems impossible to grasp the first level of the multiverse. But that's before we delve into the second level. Today, if you look at almost any illustration depicting the chronology of the Big Bang and the universe, you'll find the inflation stage at the very beginning. The concept of inflation is something we need to discuss in detail separately. But as of today, it's a widely accepted theory that helps explain certain observed properties of the universe and cosmological issues. Since the beginning of the universe, it has been expanding, but during the inflation period, it expanded very rapidly, exponentially. The inflation era lasted only a fraction of a second, from about 10 to the negative 36th to 10 to the negative 32nd seconds after the Big Bang, and in that brief moment, the universe expanded by trillions and trillions of times, possibly even more. Then inflation stopped, and the universe continued to expand, but much more slowly. But now, you might be wondering, what does this have to do with the multiverse? The Level 2 multiverse suggests, in a manner of speaking, infinite inflation. Yes, I just said it lasted only a moment, but in this concept, inflation continues beyond our universe and existed before its beginning. Imagine this as a vast space in a constant state of inflation. In certain areas, the hypothetical inflationary field responsible for inflation weakens and expansion slows, forming something like a bubble. Our universe is such a bubble, continuing to expand at a slower rate, within which stars, galaxies, etc. form. And this bubble itself is part of an endlessly expanding Level 1 multiverse, containing bubbles of observable universes, like the one we live in. There could be many such bubbles, potentially infinitely many, separated by unimaginable distances, if it even makes sense to talk about distance in this context. Interestingly, in Level 2 multiverses, there could be completely different conditions, different physical constants, and even dimensions, meaning there could be more than 3 spatial dimensions, unlike in our universe. Conditions in our universe allowed life to form, while others might be completely inhospitable for it. But in any case, this broadens the scope of the universe even further. However, again, if there are copies of you in other multiverses, there's no way to contact them. Not at all. Speaking of copies, as I mentioned, there are various opinions on this. Astrophysicist and well-known science popularizer Ethan Siegel offers a different view in his article. I'll leave a link to the article in the description, but in short, he argues that the number of possible particle interactions increases and tends toward infinity, faster than new universes appear in the second type multiverse, meaning there should not be any copies. But this brings us to the third type of multiverse, where quantum issues begin.
Wait a minute. You're sending a signal down to the quantum realm. Turn it off. Now!
The topic we're discussing is the many worlds interpretation of quantum mechanics. Now, this video is already turning out to be quite lengthy, so we won't dive too deep into the subject. But here's the gist. Quantum mechanics, which describes our world at a microscopic level, is one of the most successful modern theories. It has been repeatedly confirmed by experiments, but at the same time, you've probably heard that it's a bit odd. One of the fundamental principles of quantum mechanics is superposition, which states that a quantum system can exist in multiple states at the same time, but it only collapses into one specific state when we perform a measurement. This brings to mind the famous thought experiment involving Schrödinger's cat, or another analogy in the macro world, a coin that is simultaneously heads and tails up, and only decides which side is up when we look at it. Of course, things don't work this way at our scale. It's just an analogy. In reality, for instance, we're talking about an electron. Until we observe it, it can be, in a way, in many potential positions at once. And for example, for a hydrogen atom, it looks like this and not like that. But when we look at it, it assumes one position or state. The key point is that in the classical interpretation of quantum mechanics, observation actually affects reality, giving it a special role, which sounds quite bizarre. Therefore, some scientists support the many worlds interpretation, which suggests that at the moment of a quantum experiment, for example, when observing an electron, there isn't a collapse of the electron's wave function into one specific state. Instead, the universe splits into different universes where the electron has different states. In essence, new universes are created. This might not sound any less strange. One advocate of this idea, the renowned cosmologist Carroll, says that this doesn't mean a new universe is created every time you make a decision. If you decided to buy a burger at McDonald's, another universe where you went to Burger King instead doesn't suddenly appear. There aren't an infinite number of universes for all possible outcomes of all decisions made by every being in the universe. Universes split only when it comes to measuring quantum systems. However, according to Carroll, there could still be a vast number of parallel quantum universes that branch out. For example, when an atom's nucleus decays, or when you make a decision using a quantum random number generator rather than just deciding on your lunch spot. If this interpretation is correct, which of course we don't yet know, it implies that there are a vast number of parallel universes existing simultaneously with your copies, whose destinies may have diverged significantly. This is referred to as the third level of the multiverse, which resides, of course, in Hilbert space of infinite dimensions. Well, that's a story for another time. The many worlds interpretation sparks a lot of debate. Within the scientific community, there are both proponents and detractors, but it's undeniably an intriguing concept. It suggests the possible existence of your duplicates at an entirely different level. Earlier, I mentioned that according to Max Tegmark, there are 4 levels of the multiverse, and the last one is exceptionally extraordinary. It's the idea of universes not just in different spatial locations, but with fundamentally different laws of physics, existing outside of our space-time. Imagine a universe without quantum effects, or a universe where time moves in leaps. Well, let's not speculate further on this here. Yes, it's fascinating to ponder these hypotheses and theories. Some of them could potentially be tested experimentally, providing more definitive answers, at least under certain assumptions, somewhere in the universe, or in another universe, or in another parallel quantum reality, there might exist your exact duplicate. But of course, we cannot assert this with confidence, especially considering that we still can't definitively say whether the universe is indeed infinite.
Thank you for watching. If you enjoyed this video, don't forget to explore more of my content. I upload new videos twice a week, every Monday and Thursday. I'm Cosmo, and you're on Space Made Simple. See you next time.